Hello, computer scientists. Welcome to week 11, day 2. Just so you're clear, we will still have a final project and final exam. I've had a couple of questions on that. The final project will be remarkably similar to the midterm project, except we're going to be using MongoDB. The last couple weeks of the semester are going to be using MongoDB to create a project. I am going to make partner work optional, but highly recommended. So I'm not going to force people to have partners, but I would strongly recommend it because that is the way you are going to work in the real world, and it'd be useful to practice that now. The only caveat is you cannot use the same partner that you had for the midterm. So if you want to have partners, then you're going to have to work with someone new. The final exam is going to be the same format as the midterm exam. It's going to be take home. You're going to have a week to do it. There's going to be no late work allowed, and it's open book, open internet, open notes. You just have to show me that you understand the question or the material, and you have to cite your sources. So today we're going to talk about distributed MongoDB systems. There's no specific homework for today, but this will be on the final exam, so you will need to understand it. Setting up distributed systems would take you more time than I want to spend this week, but you still need to understand it in theory. There's still the homework from Tuesday that is due in 4 days, next Tuesday. So, all right, so distributed MongoDB systems. Typically, when you have distributed databases, there's a few issues that you have to think about, right? So if you have just your traditional SQL database and you're a worldwide company, you have servers in several different countries, and you have to think about these issues, right? You have to copy your data to all these different locations. If you remember in class, we did a little bit of that where, you had a couple of servers trying to stay coordinated, and people constantly adding and changing data. It's tricky to do that, as we learned in class. And then there's, what if one site goes down? What if your, data center over here in Europe has a fire, or just the power goes off for an hour or two and then comes back up? How do you deal with that? Failure of communication links. What if, the data line between North America and Europe just goes down for an hour or something like that? So, we had that happen in the real world. A big ship was pulling out of harbor and dragging its anchor, and it actually severed the internet lines. So that does happen. And then, you've been updating data in both servers at the same time. How do you synchronize that? How do you reconcile that? What do you do when somebody does a commit to, adds a tweet to the Twitter server in California? How do you get that information to all these other servers? What if, a bunch of different people update the same data on different servers at the same time? Right? So that's a distributed deadlock. That means, several people or several systems updated the same information faster or within a smaller amount of time than it takes to communicate those changes between the servers. So say, just as an example, it takes 5 seconds to transmit all the changes from California to all these other servers. What if within that 5 seconds somebody else has changed the data and it's sending it back, right? So who wins? What is the real data? These are really hard issues that people database administrators have to deal with. So one of the ways that they can be dealt with is you have a primary site, right? So you have this server in the middle here that is the primary server, and it is the master, if you will. So anytime you want to update your data officially, this guy has the official data. So it's not done until this server has done it. So if I update my Twitter feed over here on this server, it's not updated until it gets here and updates this. So if somebody over here and somebody down here both update the same piece of data, whichever one gets to the main server and updates that first, that's the real data now, and it will send it back out to all the other servers. So even if this person updated chronologically first, if this guy down here gets it to the main server first, he'll send it out to this guy and overwrite whatever he had, because this main server is the priority server. Obviously, that involves a lot of overhead, right? Because every change you make to any one of these has to get sent back to the primary server and then sent back out to all the other servers. So these networks have to be really, really robust. And also, there's a single point of failure, right? If this guy dies, we no longer have an official copy of our data. We don't know what the state of our data is, which is a bad thing in database management, right? You never want to be in a situation where you don't know what the status of your data is. So you need to make big backups of this, and then of course, if you have backups of this, every backup you have running in real time is going to double the amount of communication required. Right? And there are tricks around this, obviously, to lessen the load, but still, it is a huge amount of communication overhead. So MongoDB kind of does this. If you choose that way, it creates a primary, which is the official server. So you still have a primary machine that has all your official data, and it still does communicate between all the other servers. So you still have this idea of a main server, and then you have all these secondary servers. And what happens ideally is that the primary server is written first, and then all the replicas are written. So the idea is that in this case, you're going to be reading from these other guys, but you're going to be writing to your primary server. And that kind of keeps the load a little bit more distributed and also keeps the primary updated. If the primary fails, what they do is they have an election, and this is all obviously in software. They don't sit there and wait for humans to do this. But they, depending on the algorithm they're using, they create a new primary, right? So if this guy goes down, in this case, there's 6. So ideally you have an odd number so that there's always a majority, but you can have an arbiter machine. But basically what happens is they decide based on speed of connection and size and a whole bunch of other things that we're not really worried about, to elect a new primary server. So this can happen on the fly. If this guy goes down, then all these other guys elect who's going to be the new primary. Let's choose this one up here, and essentially all these connections then are going to this new primary. This new primary becomes the one that has the official data and sends it out to the other servers for reading. And again, I'm going to say it depends because you have different scenarios. What might happen is these are all in the same building. You might use a different algorithm than if they're spread across the world. So again, I'm not worried about the implementation details. What I want you to understand is how replication works across, like, imagine across the world, what the issues are when you're trying to run multiple databases at the same time around the world. So you can have local, which means that I only am interested in the data on my local machine, or my priority is the local machine. You can say majority, which means make sure that the majority of these servers agree, or linearizable, which just means that the data, like I'm searching linearly through this to get the most accurate data. But again, it depends on your use case. So for most use cases, we're reading a lot more than we're updating. So we want to make sure our primary has the latest data, and we're reading from whatever is the fastest server for us. So here's an example of using a primary system. Maybe most of your users are in Europe, and so most of your data is being updated in Europe, but you have lots of users around the world, so you have replicas in, I'm not sure where this would be, maybe Japan, South America, North America, Southeast Asia, not sure where that would be. But point being, you can replicate your server if you put all of your data in all of these locations, and you have a primary that's in charge of making sure that they're up to date. So one of the other issue that you have, right, is say you're a small company and you build a database and you're happy with your database. Maybe it's just sitting on a server in your parents' basement, and all of a sudden there's a New York Times article about your company, or say you're Zoom and all of a sudden there's a pandemic. Who could imagine that? And all of a sudden you have 100 million people trying to use your software all at the same time, right? You're going to need to take this database that you thought had way more space than you'd ever need, and you're going to need to make it much bigger. So in a traditional database, in a relational database, you're basically going to need to take that server and make it into a really big server. You have one with small space, small memory, and you make it huge. And there's lots of ways to do this, right? Like the way that Amazon Web Services and Google and stuff do it is they make a giant virtual machine that might actually be running on several smaller machines in the background. But it looks to us like it has, 100 CPUs and 128 gigabytes of RAM and 100 terabytes of disk space and blah, 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 blah. So it looks really big and it costs a lot of money, right? And yeah, there are other ways you could do it. You could try to split up your database into multiple machines if, you sort of have some logical way of doing it. Like you don't want to split up your customers and sales tables onto different machines, because you're going to be joining those a lot. And to join a database across machines would be incredibly slow, right? It would be horrible. So one of the power of SQL is also its weakness here in terms of expansion is when you're doing all these joins, they have to be local, right? You have to have all those tables on the same machine, or it's going to be death by slow, right? You're going to not be able to join those tables fast enough if your issue is that you're growing too quickly, right? So you kind of need everything on one big machine. So what MongoDB does instead, and yeah, you can do this as well with MongoDB. You can just buy a bigger machine, but from the start, the idea of using commodity hardware to grow your database was built into MongoDB. So you have this small machine, and all of a sudden you have a huge database. What you do is something called sharding. And so you use the MongoDB software to split your data into sections that then you can each put on its own small machine. So this can be across a single collection, right? In SQL terms, in a single table, it's going to take 10 rows and put them on this machine, 10 rows 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 on this machine, right? And so you can have as many of these as you want, and MongoDB will automatically split it so that an equal amount goes on each of these small machines. And from a user perspective, this is all invisible, right? So you don't even need to know that your database is running on 5 machines now. As far as you're concerned, it looks just the same as it did before. The key, of course, is how do you split these up, right? How do you split the data up so that it is usable, so that it is, fast? And there are a few ways of doing that. So we're going to try and scale our database across many small computers instead of trying to buy a much bigger computer. And the two main ways of doing this are called range partitioning or hash partitioning. And so you have to, shockingly, think about how you're going to use your data. If you know, for example, that you have a pretty good distribution across one of your keys. So if, for example, you're often going to look for a range of people by their social security number, right? Then social security number is a pretty good key because it will split people pretty evenly across, these different shards, right? It's not like there's a whole bunch more people with a social security number that starts with 111 than there are with all the other ones. Dates can be a good one if you have a pretty good distribution of dates, right? It's a little bit dangerous to use dates in something like Twitter because then 99% of your usage is going to be on one shard, right? It's going to be the most recent. Nobody cares about tweets from 10 years ago. Literally nobody. So you want to be a little careful when you're developing your key that both, the inserting and the updating and the reading is kind of balanced. It doesn't have to be perfect, right? You're going to let MongoDB handle most of that. But you want to think about how you are using your data and have it spread out across, shards. So maybe birth dates for employees or something would be a good sharding technique, right? Because then you're going to have a lot of different birth dates spread out across, these shards. But it also, it needs to be a key that you're actually using, right? So if you really want it to be randomized, right, you might want to use a hash partitioning. And if you remember hashes from when we were talking about passwords, right, it takes a piece of data and gives you an associated number. So you might have different data with the same number, but overall, you're going to have buckets that are pretty even. So say, for example, you hash by last name. All you'd have to do is take say A is 1, B is 2, C is 3, D is 4, blah, 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 and you add up the number value of the last name. So like Bartus would be 2 plus 1 plus, oh, what's R? 20 something plus blah, blah, blah. And I get some number at the end, and that's my hash. That's the number of the bucket that I put my information into. Somebody else will have that same number with a completely different last name. And that's okay. But what's going to happen over the course of all of my data is it will pretty evenly split all the last names into different numbers. And then I just take numbers 1 to 10 go into my first shard, numbers 10 to 20 go into my next shard, numbers 20, whatever it is. But it's kind of a pseudo-random way of splitting up my data on and putting it into even buckets, because you want your shards to be about the same size. You don't want to have one shard like the Twitter example I had, where you're using 90% of your data, because that completely defeats the purpose, right? The whole point of shards is you're distributing load across multiple small servers instead of having to buy one big server. So basically what I want you to get away from what I want you to do is you want to have a key that splits up your data so that the usage is pretty even across all of your little shards. And you have to think about what the best key would be for that. It doesn't have to be the same thing you're always searching for. It just has to be a way to distribute the load. And what's going to happen, right, is you have your apps here, and you have lots of people using your app. These are still going to go through what's called a query router or a balancer. And what it's going to do is it's going to tell it where to get its data from. So this doesn't do anything except sort of manage that key and manage those shards so that all your apps know where to go. And this is what makes it transparent, right? This, for our app, looks like one big MongoDB database. The apps don't know that it's actually a whole bunch of shards. The apps think that, let me put it this way. If you write an app for a MongoDB, and then unbeknownst to you in the background, your database administrator has sharded that MongoDB database, your app will still work fine. Right? You don't have to change anything in your app, which is nice. So the problems with this, though, right, is that you now have your data in multiple different systems, right? So if I have my university database, I might have 10 students in my first shard, 10 students in my second, 10 in my third, 10 in my fourth, whatever. It's no longer one big table that I can just lock and update, right? So for example, I want to, the bank transfer idea, right? If I want to transfer $100 from account A to account B, what if they're on different shards? Right? How do I make sure that the bank transfer happens in an atomic transaction if they're on different computers entirely, right? That's a hard problem. It's not for the application developer because they just do it and expect it to work. But as far as the MongoDB database administrator is concerned, you want to make sure that it works the way they expect it to. So basically, what happens is if you're trying to do a transaction, right? Think of it as a transaction in SQL that has to be atomic and consistent. Then the MongoDB software will try to lock those shards. And so as long as the there's no other lock already on those shards, it'll go ahead. And so no other transactions can occur as long as those shards are locked. So if I'm going from transferring money from Alice to Bob and they're on different shards, I'm going to lock down those two shards so no one else can change Alice and Bob. If I can't get that lock, what happens is it just times out. It says, no, I can't do this transaction. I'll try again in 10 milliseconds or whatever it is. So it'll keep trying a few times to get that lock because, you know, these transactions are extremely fast. So if it can't get it right away, it'll get it, you know, the next time. And so it locks those shards, says nobody else can do it. It does its transaction, and then it releases the lock. Right? So the lock, remember, is only for writing. So the reads can keep going ahead, right? Until we're actually changing data, right? So as long as the data you're interested in is not changing, you can keep reading. So it doesn't like lock the entire database down. All it does is lock the two shards that are Alice and Bob are part of, so that nobody else can update them while I'm trying to update them. So it's a really fast process. You know, it does involve a little more traffic because I have to request the lock on those two shards or three shards or five shards or however many I'm updating, right? I have to get the acknowledgement, then I have to send my transaction. I have to get the, you know, acknowledgement that my transaction succeeded, then I have to release the lock, and then other people can update. So it's very fast, but it also, you know, is traffic heavy. But that's what allows atomicity and consistency across multiple documents and shards, is I have to be able to know that nobody is updating the same data as me at the same time as me. So those are basically it for the things you need to know about distributed Mongo systems, right? To kind of recap, I want you to understand how distributed systems work for SQL in terms of what are the issues, and we talked about that earlier in the semester. What are the issues for if you're just replicating the same data across servers, and that is the same for MongoDB and SQL, right? So if you just have the same data on 5 servers around the world, right, then the issues are the same. It doesn't matter whether it's MongoDB or SQL. But when you are expanding your database, right, you're taking it from a small database to a big database, right, the issues are different because SQL, you kind of have to stay on one big system. In MongoDB, you can split up into multiple small systems in the background, even though it still looks like one big system to the user. So, two different issues here about how you expand your systems, either copying your data to multiple systems worldwide, or in the case of MongoDB, splitting it up so that you don't have to buy bigger and bigger and bigger servers. You just keep adding more small shards. And I'll add some links so that you can read more or watch some more videos about that. Thanks, and I will see you next Tuesday.